All right, so we are recording, and we're going to talk right now about something called linearly independent sets or bases, which is an extremely important concept in linear algebra. So there's a concept of, let me see here, hold on. One moment. Let me check just one thing here. Okay. So linear independence is a concept that you learned, let me see, I'm trying to find the section where you learn that. You learned about when a set of vectors was linearly independent. And that, according to my information, is back in section 1.7. And that's right, that's where you learned about linear independence and linear independence. So a set of vectors are, as you are aware, are linearly independent if you have a linear combination of those vectors and you set it equal to the zero vector, then the only solution for those coefficients, C1, C2 up to CP, are they're all equal to zero. That's the definition of a set of vectors in a vector space being linearly independent. On the other hand, if not all of those weights, C1 to CP, if they're not all zero, then you have a set of vectors that are linearly dependent. And this concept is extremely important because it helps us establish the definition of a basis. But just a comment here, a theorem that is, I think it's pretty much common sense, that if you have a set of vectors, if you have a set of two or more vectors, okay, and the set's linearly dependent, well, of course, that means one of the vectors can be written as a linear combination of the other vectors in the set. I mean, I think that's intuitive, and that would make sense, because if you have vectors that are linearly dependent, that means they're related to each other by the fact that some of the vectors in the set are linear combinations of other vectors. And well, and actually, I want to be careful how I say that. Actually, every vector in the set would be a linear combination of a set of other vectors in the set. But in theorem 4, they're just basically saying that they're saying that, like, you could start off, like, if you had say you had 5 vectors in a set, and okay, the second vector is independent of the first vector, the third vector is independent of the first and second vector, linearly independent. Eventually, either the fourth or the fifth vector would have to be able to be written as a linear combination of those preceding vectors, if the set of vectors was linearly dependent. So it's just a theorem that is intuitive. And if we hold on here, let's look at a few examples here. So here you have 3 polynomials, okay? 3 polynomials in the regular polynomial P1 space. They're all first-degree polynomials. These set of vectors then are linearly dependent in that space P, because the third polynomial can be written as 4 times the first polynomial minus the second polynomial. Okay, so that's a linearly dependent set. Are there any questions on that? All right, well, let's look at the second example because it's nice to see some, new kind of examples. You could have a set where your elements are the sine of t and cosine of t. In other words, those are your vectors, those two functions. And that is a linearly independent set because the sine of t and cosine of t are not multiples of each other. Okay, not multiples of each other. But let's say you had a set like this. Let's say you had a set where you had a sine of cosine t, sine of t, cosine of t, and sine of 2t. Well, that set is linearly dependent because sine of 2t equals 2 times the sine times the cosine. So one of the vectors, I want to say it's the right way. Hold on. I want to be a little bit careful here on this. The thing is, I want to think of the sine of when I think of linear dependence, I think of one of the vectors as a linear combination of the other two vectors. Like in in this case, we have three vectors, three functions, and one of the functions, if the set of functions is a linearly dependent set, the one function should be able to be written as a linear combination of the other two. And I know that the identity sine of 2t is 2 times the sine times the cosine. We know that. But see, like if the third function were like if you had this, okay, think of it like this. If you had this, let me go to the whiteboard here. If you had something like this, say you had the sine squared of t, the cosine squared of t, and 1. Okay. Would that set of functions be linearly independent or linearly dependent? Dependent. That's right, Hung. And why is that? Why is that? Well, good, Benjamin, the identity. Good, Hung. So 1 times the sine squared of t plus 1 times the cosine squared of t minus 1 times 1 equals 0. See, that's how I think of linear, that's how I think of it. I mean, I take a, but you could think of it, maybe that isn't the right way. I'm not saying that's wrong, but think of it like this. Let me think of it in terms of the way we think of it in differential equations in Math 282. So, which they're actually learning this now, or have learned that, just learned that. You see, the number 1 is equal to sine squared plus 1 sine squared plus 1 cosine squared. In other words, this third function in the set can be written as a linear combination of the other two functions, and therefore the set is linearly dependent. This set of functions is a linearly dependent set. And so that's absolutely how I'm used to seeing it. This this example 2 in the book, if I go back to that example now, is actually something I hadn't thought about really in terms of linear set being linearly dependent, because the sine of 2t is the product of those two functions. Normally, I don't think of linear. So in example 2, since the sine of 2t equals 2 times the sine times the cosine, they're saying that set is a linearly dependent set. That set of three functions. So I can accept that, but it's not normally what we're used to seeing. I'll just tell you that, okay? So I don't think example 2 is really I mean, right now I'm not actually entirely comfortable with that example. I'm gonna think about that more. But the thing I did on the whiteboard, I'm very comfortable with. But let's continue on here. So now a basis. So suppose you have a subspace H of a vector space V. An index set of vectors is a basis for that subspace H if the set of vectors, script B set of vectors there, B1 up to B2 up to BP, if the set of vectors has to be linearly independent, and the span of the vectors has to be equivalent to the space H. So H is the space H, you'll have a basis for your subspace H if H is the span of the vectors, okay, in the basis. I want to be careful how I phrase this. If you have a set of vectors, B1, B2 up to BP, and the span of, and I'm not saying this the right way. Let me say it a different way, okay? Let me do an example to reinforce this, okay? Let me do an example here. Let me go to the whiteboard again. So let's say that you have the vector 1, or you have the set of vectors 1, 0, 0. And 0, 1, 0. Okay, and let's say the span of those two vectors is, I'm going to call it space H1. Okay. Okay. So and let me see here. One moment. Let me try my pad here. One moment. Okay. Is H1 a basis for R cubed? In other words, is the space H1, which is the span of E1 and E2, which you also like to know, you like to call it I and J. Is that subspace H1, is it a basis for three-dimensional space? Okay, I'm getting, Haley says no, Benjamin says no. That's correct, it's not. Well, what's the problem? What's the problem? You know, we might wonder why. Well, we do wonder why. Well, let me ask you this. Okay, Haley says any vector, hold on, let me bring her thing up. Any vector in R3 without a 0 for its third entry cannot be created through the linear combination of those two vectors, E1 and E2. Excellent, Haley. That's exactly right. That's exactly right. Okay. So, I mean, if you have, I want to say this the right way. I want to say this the right way. So H1 here, hold on. I'm sorry, this thing's acting crazy. I'm going to hold on, get my mouse back. See, the definition talks about, well, all right. I mean, I know what I want to say. I just don't want to, I want to make sure I'm not confusing anybody. So if this space H1, if this subspace, well, how would you describe, let me ask you this, let's do it geometrically. How would you describe this space, this subspace H1? How would you describe it? It's a subset of three-dimensional, it's a subspace in three-dimensional space. But how would you geometrically describe that space H1? Okay, good, Benjamin. A plane. All right, a plane in with a plane with what like axes? Is it a horizontal plane? Is it a vertical plane? In other words, okay, good. H1, good, Lewis. Hung those two. H1 is literally the x1, x2 plane. In R3. Okay, but clearly the R3, you can't take, if you were to take any vector in subspace H1, okay, that vector is going to lie in the x1, x2 plane. And as Haley commented, if you were to have a vector like, say you were to have a vector like 2, 4, and -5, that vector is not going to be in this span. Okay, so H1 cannot be a basis for all of R cubed. All right. What if we had this, though? What if we had the span instead of 1, 0, 0, 0, 1, 0, and 0, 0, 1. I'll call that H2. Okay. In this case, is this subspace, and we know H2 is a subspace because it's a span of vectors. Anytime you have a span of vectors, that span is a subspace. Is H2 a basis for R cubed? So you have here E1, E2, and E3. Is the span of those unit vectors a basis for R cubed? Well, let me ask you, are the three vectors here, are these three vectors linearly independent? Is E1, E2, and E3, are they linearly independent? Okay, hold on here. Let me just bring up the chat here. Hold on. Okay, that's right, Hung. Yes, So, I mean, is everybody okay that those are linearly independent? I mean, that was kind of, I'm hoping that was an easy question. I'm hoping that was an easy one. Yeah, they're linearly independent. All right. Well, can any vector in R3 in three-dimensional space be written as a linear combination of E1, E2, and E3 vectors? Like 2, 4, negative 5. Okay, 2, 4, negative 5. That's a vector in R3. It wasn't in the span, it wasn't in subspace H1, but is it in subspace H2? Is this vector here, 2, 4, negative 5, is this vector in subspace H2? Can this vector 2, 4, negative 5 be written as a linear combination of E1, E2, and E3? The answer is yes. That's right, Nafani. That vector is going to equal something E1 plus something E2 plus something E3. Okay, what are the numbers going to be? Good, 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 Hung, good, Nafoni. 2, 4, and negative 5. Absolutely. So does it seem clear? I mean, we did it for one vector, but does it seem clear that any vector in R3 will be in subspace H2? Does it seem clear that any vector in R3 can be written as a linear combination of these three vectors, E1, E2, and E3? We know the three vectors are linearly independent. But do those three vectors, is the span of those three vectors equal to R3? Can any vector in three-dimensional space be written as a linear combination of E1, E2, and E3? Yes, that's right. So therefore, this subspace H2 is a basis for R3. And in fact, it is it is equivalent to R3. Okay, let me do another little thing with you. Are there any, is this helping? Is this helping, this little kind of these little examples? Are they helping you? Good, good, good. Well, let me do another one here. Let me bring up the. I guess I have to bring up a new whiteboard here. Sometimes, you know, it kind of scrolls down, but all right. Let me bring up another one here. What about this? What about this? Suppose you have a space H that equals the span of 1, 0, zero, 1, and 2, 3. Okay. Okay. H is a subspace of R2 because H is defined as a span of a set of vectors. So H is automatically a subspace. Now, is this subspace H a basis for R2? Why not, Hung? Oh, well, actually, we got difference of opinions, which I like. I appreciate all participation. But there is an issue, and that's right. That's right, Haley and Hung. This set is not linearly independent. Okay, this set is not. I want to say this the right way. Let me call this E1, E2, and V1. Now, to be sure, maybe, Ben, this is what you were thinking, any vector in R2 could be written as a linear combination of these three vectors. Okay, some linear combination. But this set of vectors, E1, E2, and V, I call it V1, okay, this set is not a linearly independent set. It's not linearly independent. And because of that, well, and why is that? Why is that? Well, can we relate vector V1? Okay, and maybe I'll just call it vector V. We don't need to have a V1 there. It's the only vector in there. There's only V in there. Good, Hung. V, very good. V, that vector V, equals 2 times E1, 2 times vector E1, plus 3 times vector E2. Okay, so that means then, hold on. You could also think of that, incidentally, as 2 times E1 plus 3 times E2 minus 1 times V equals a zero vector. In other words, you have a non-trivial linear combination of the three vectors that equals a zero vector. And so you have a, don't worry about that line. I don't know, it pops up sometimes, I don't know why. But you have a non-trivial linear combination of these three vectors that equals a zero vector. And so by definition, the set of vectors is not linearly independent. The set of vectors E1, E2, and V is linearly dependent. And that means that it cannot be a basis for R squared. Think of it like this. Do we have too many vectors? I mean, for a basis for R2, I mean, E1 and E2 are good. Good, Benjamin. But now you threw in this extra vector that you didn't need. You don't need that vector 2, 3. You don't need it, right? And it's like doesn't add any information to the geometry of the space. So in a sense, a basis is a very conservative. Well, I'm going to say it's the right way. Hold on. There's a word I'm looking for. Hold on, one moment. Yeah, a basis is a spanning set that's as small as possible. In other words, you only need, even though these three vectors themselves, okay, will span R2 space, you don't need that last vector V. You don't need that to span R2. So a basis is a spanning set that is as small as possible. That's how you can think of it. Okay, are there any questions on this? How many found this? Was this example helpful? Excellent, excellent, excellent. And a lot of times, thank you, Nafani. A lot of times to help you, to help feel comfortable with concepts, it helps to create little examples. I did that in graduate school all the time with statistics. Now, nobody told me to make up the examples, but I made them up to help me learn. And in four-year college as well. So okay, well let's go then back to the book here and keep going down. So now we have an idea in our mind of what a basis is for a space. And in example 3, they say, suppose you have an invertible n by n matrix A. Okay, so the matrix A consists of the column vectors A1, A2 up to AN. Then the columns of A have to form a basis for Rn. Okay, they have to, because if your matrix A is invertible, then the columns of that matrix A are linearly independent, and they also span Rn by the invertible matrix theorem. Remember the invertible matrix theorem, you learned that back in section 2.3. So you see, you can use the invertible matrix theorem sometimes to help you establish if you have a basis. Okay, you can use that. Okay. Are there any questions on that? Okay, well, let me go to, let me see here. Let me go to, let's see here. All right, let me go to I'm going to go to example 8 here. I want to go to example 8. So let me go down a little bit here. Whoops, I went too far. Oh, I went way too far, didn't I? Hold on. I'm sorry, class. I'm just trying to find where I'm at here. Hold on. All right. Let me just use this. It's a little tedious, but see here, the spanning set theorem. A basis is an efficient spanning set that contains no unnecessary vectors. No unnecessary vectors. So I'll tell you what, actually, I think what I'm going to do is I'm going to go here to an example that I made up to help you. Let me go to that example. Okay. Let me give you a moment to copy this example down, and then we'll talk about it. Okay, so we want to find a basis for this space. The space H is defined by the span of those 4 vectors. Okay. So let's see here. Let's look at these 4 vectors. Do you see anything interesting? If we look, for instance, at the second vector and the third vector, is there something interesting? That's right, Benjamin. The vectors are scalar multiples of each other. So if we want a basis for this subspace H, do we need both of those vectors? You know, in other words, if I were to, let me just maybe I'll put like, I'll label this is A1 vector. Here's A2 vector. Here's A3 vector. And here's A4 vector. And Ifani says, oh, well, for a basis for this subspace H, we're not going to need both A2 and A3. Okay. What about A1 and A4? What about these 2 vectors here, A1 and A4? Is there redundancy there? Absolutely. Absolutely. I mean, well, we already established that A3 is equal to 2 times A2. And good, Nafani, A4 is equal to 2 times A1. Okay, so there's some linear dependence in this set of vectors. Okay, and so we don't need all 4 vectors to have a basis for space H. All right. So let me just see here. Let's look at it another way, okay? I'm going to construct a matrix A with the 4 vectors in subspace H as the column vectors of the matrix A. And what we're going to do is we're going to try to solve this vector equation to examine the linear dependence relationship between these vectors, these 4 vectors, A1, A2, A3, and A4. Now, we were able to observe the linear dependence relationships and write them out just by observation. And that, you know, we just had 4 vectors. But what if you had a set of vectors where you had 100 vectors, you know, or, you know, 10 vectors? we need something. We need a way to. We need a little bit more formal way to help us. So let me give you a moment to copy up to here. Okay. And incidentally, class, I'm told that if you click on your screen a few times, it will enlarge the handout, I guess. I don't know if it, now watch, it won't work for me, but it was working the other day. If I click a few times on the screen where the page is, it'll enlarge the page. It works, all right, Hung, it works, all right, good. Well, that's something new I learned. I mean, normally I try to write large enough so that, you know, things are good, but hey, you know. All right, so let me give you a moment here. Okay. All right, so the reason I'm interested in this vector equation, x1 times a1 plus x2 times a2 plus x3 times a3 plus x4 times a4 equals the zero vector. The reason I'm interested in that is that I want to say this the right way. The linear dependence relationship between the four vectors can be established based on this vector equation, where the weights are x1, x2, x3, and x4, because that comes from the definition of determining if vectors are linearly independent or dependent. We need to establish what the weights are, x1, x2, x3, and x4. Okay, and if yeah, so what I do is I set up the augmented matrix here based on the vector equation here. Okay, I set it up, and I left out the row operations here, but if I do the row operations and get the augmented system in reduced row echelon form, so which would be then, well, the augmented matrix A0 becomes the augmented matrix B0, where the matrix B is this matrix with vectors B1, B2, B3, and B4. Okay. And you see, it's okay to do that because, I mean, if we're trying to, again, think if you had a matrix that were large. Let's say you had a lot of vectors. You had a big set of vectors, and you wanted to see if those vectors formed a basis for your space. Well, you'd have to check and see if the vectors were all linearly independent. And if not, what are the dependence relationships among the vectors? You need, and if there is dependence relationships, you need to find that so you can determine what vectors you can exclude from the set for you to have a basis. So when we do the row operations and reduce the augmented matrix into reduced echelon form, the resulting columns, the resulting column vectors, B1, B2, B3, and B4, it's very interesting what happens, because how is B3 related to B2? How is B3 here? How is B3, vector B3, related to vector B2? Right. Good, Hung. B3 equals 2 times B2. Just like uh, vector A3 was equal to 2 times vector A2 back when we looked at the original, we constructed, if you look here now, remember A3 is equal, vector A3 equals 2 times vector A2. Well, here vector B3 equals 2 times vector B2. Cool, huh? All right. Well, in our original matrix, vector A4 was equal to 2 times vector A1. Well, when we reduce the system and get here, vector B4 is 2 times vector B1. So in other words, row operations preserve linear dependence relationships among the column vectors. And you see, when you get the matrix here, we have this matrix B that's in reduced row echelon form. Is it easier to see, to observe the linear dependence relationships between the column vectors of B, or is it easier to observe the linear dependence relationships between the column vectors of A? Okay, so think about the linear dependence relationships between the column vectors of the matrix A. Think about the linear dependence relationships between the column vectors of the matrix B. Which is a little easier to, if we want to determine the linear dependence relationships between column vectors, is it easier for the matrix B or the matrix A? Which is it? Oh, a little bit easier. Good, Hung, matrix B. Now, it wasn't hard. Matrix A, it wasn't hard. But the point is that matrix B, it's absolutely the easiest. And this would work if you had a huge matrix and then you put it in reduced echelon. You'd say you had a huge matrix with a lot of column vectors, and you don't know what the linear dependence relationship is among those column vectors. Well, if you get that matrix in reduced echelon form, the linear dependence relationships between the column vectors of the matrix in reduced echelon form is equivalent to the linear dependence relationships between the column vectors of the original matrix. Okay, so essentially by row reducing a matrix, you can determine its linear dependence relationships of the column vectors. How many think that's apps? And I actually, I mean, below here, I wrote in a comment. That's something I had mentioned. I talked about that. How many think that's absolutely cool? Okay, Hung likes it. Maybe we get a few more people. All right, Nafani likes it, definitely. And anybody else? Okay, thank you, Abby. All right. It's nice to have three. It's nice to have three. Now let me ask you this. If we let's focus here on let's focus on the vectors. So hold on. So what vectors are going to form a basis? I mean, originally here, right, this was the problem. Find a basis for the span of these four vectors. What vectors here, okay, form a basis? So, you know, a basis for H. For that space H. What vectors? Okay, that's right, Nafani. A1 and A2. A1 and A2. Geometrically, what is that basis look like? What is the span of the vectors A1 and A2? We don't need A3. We don't need vectors A3 and A4. They're redundant. What would the span of so the basis for H is right here. The set of vectors A1, A2, and what would that span look like? What would that basis look like? Where does it live? Where does it live? Does it live in two-dimensional space or three-dimensional space? This basis. Well, where do these vectors live? Do these vectors live in R2 or R3? That's right, Nafani. They live in R3. And, okay, geometrically, what would the span of those two vectors be? That's right, Lewis. You would have a plane in R3 passing through the origin. Okay, you would have a plane in R3 passing through the origin. Are there any questions so far? All right. Well, let's look here. Let's go down to you know, the matrix B here. So for the you know, B1 and B2 are the corresponding vectors to A1 and A2. Let me ask you this: let me ask you this. Let me try my little thing here now. Let me try my little pen thing. I just got to avoid touching that one button. It like goes haywire when I touch it. Hold on. All right. Does the span of A1 and A2 equal the span of B1 and B2? So we know the span of A1 and A2 is a plane in R3 passing through the origin. Okay. How would you describe the span of vectors B1 and B2? I mean, that's a plane passing through the origin also. And what would the orientation of that plane be? Would it be vertical? Would it be horizontal? Would it be like at an angle? Okay, that's right, Hung. It would be the span of vectors B1 and B2 would be the XY plane. The XY plane. Because you have those two vectors are in the XY plane. Is the span of the vectors A1 and A2 the XY plane also in R3? Is the span of vectors A1 and A2 also the XY plane? No, that's right, definitely not. So you have to be a little careful about that, because sometimes what happens is students, they'll like, for instance, you have a problem where it says find a basis for a column space of a matrix, and you set up a matrix with the column vectors, you do the row operations, and students will sometimes think that these vectors that result after you do the after you get the matrix of vectors in reduced echelon form, they sometimes students will mistakenly think that the vectors, the final vectors, are the basis vectors, but they're not. They just those signal what the basis vectors are in the original matrix A. Okay, are there any questions on that? Yeah, I agree, Lewis. It is incredible. Well, and this is a reason why I don't want you to forget about how to do row operations, because row operations preserve the linear dependence relationships among the column vectors of a matrix. And it's good to have an intuitive feel for that. Okay, so I want to do another example with you, but this one I might just kind of go through quickly. I mean, it'll be in the notes, but you don't really, I mean, have to copy it down, okay? Because I want to give you some class time to work a little bit here on section 4.3. So this one, let me just go here and talk about this. So don't copy this. It'll be you're going to be practicing plenty of problems, but on this. But here they want you to find a basis. Well, nah, go ahead. Yep, go ahead and copy it down. Yeah, let's do it right. Here. All right, so let me give you a moment to copy this. Okay, so we want to find a basis for the null space of a matrix. And how do we find the null space of a matrix? Okay, how do we find the null space of a matrix? So what consists of the null space? A times something equals something. Okay, what's going to go in the little circles here? Maybe that's, let me do it this way. Now I'm looking for the null space of matrix A. Okay, so that means, that's right, Benjamin, I got to solve this system. A times X equals a zero vector. And keep in mind, the matrix A is 3 rows by 5 columns, right? So the vector X is going to be what? What would the dimensions on the vector X have to be? Five by 1. Good. Okay, okay. And then, of course, the zero vectors are 3 by 1. But the point is, maybe I'll put that in blue, 3 by 1. But the point is, you know, I like to know things, any information I have to help me understand, you know, what I'm doing is good, right? So the fact that the null space, how do I find the null space? I solve for this solution vector X to this matrix equation, A times X equals 0 vector. And the solution vector X, which will determine my null space of the matrix A, that null space lives in, well, the null space of A is a null space of A is a subspace of what space? The null space of A is a subspace of R what? R5. Good, Benjamin. Has to be, right? Has to be. Because the solution vector X is going to determine our null space. And that is a 5 by 1 vector, so the null space has to be a subspace of R5. So, of course, what we have to do here is solve that matrix equation. And what I did, okay, well, and I actually went through and solved it. I did the row operations here. Okay, so we don't want to forget our row operations. So take a moment to copy this down. You know, I start off with the augmented matrix here and do row operations to get the augmented matrix in reduced echelon form. So let me give you a moment to copy that down. Okay, and while you're doing that, uh, just a reminder to be sure to check your MC email in regards to, I sent an email, let me see here, one moment. Yeah, the email was sent late last night in regards to how I want students to submit their work for the exam. So be sure you check your email, your MC email. Look for my email that talks about how to submit your work for the second exam, and that will basically lay out how I would like it done. And Nafani, did you have a chance to check that out, that email? I know everybody's copying. I'm just asking. I saw Benjamin and Nafani sent me a attachment. Benjamin, you saw the email, right?
I saw it.
And you saw it. All right, good, Nafani. Excellent. Excellent. Yeah, I'm sorry I didn't get it a little sooner to you all. It took me a while to kind of figure out how I wanted to do it, and I had to do some experimenting with like sending PDF files to myself to see if they would, if they would upload, and pretty much up to 25 megabytes it worked. But sometimes students, depending on how they, sometimes the work, they use colors and things like that, and it's very nice. But it takes up more space, but that's fine if the work is done as I recommend, submitted as I recommend. It shouldn't be a problem. All right. So, okay, so we do the row operations and we get down to here. And remember, this is an augmented matrix, right? It's an augmented matrix. We have two equations, two different equations here. With 5 variables. So how many free variables are there going to be? Have to be 3 free variables. That's right, Abby, and I appreciate all, again, all responses. You have 2 different equations with 5 variables. You're going to solve for each variable. 3 of them have to be free. Good, good. So let's go now. What we're going to do is we're going to determine what the null space is by writing the solution of this augmented matrix in what special form? What special form? It begins with a P. Parametric form. Excellent, Haley. So may I go to the next page and show you that? Okay, I assume all the instructions here are fine on the row operations. All right, well, so we're going to have this. This is the system you're going to have. This is the system you're going to have based on the augmented matrix. Okay, and so based on then the first equation, I'm going to let x4 and x5 be free variables. So x3 will equal negative 2x4 plus 2x5. And then going to the first equation, well, I'll let x2 be free. And then x1 is 2x2 plus x4 minus 3x5. Okay, and so I write, I mean, again, this helps me to, here's my vector x. My vector x consists of 5 variables. Oh, what are those 5 variables? Here they are. Here they are, based on what I did up here. And then I write the solution vector x in parametric vector form. Let me give you a moment to catch up here. Okay, so my solution vector x, which contains all the information about the null space, okay, is written in parametric vector form here. And the vectors u, v, and w, you'll notice they are automatically linearly independent. Okay. So that's true. Whenever you, well, if you get the matrix in reduced echelon form, if you get your augmented matrix in reduced echelon form when you're looking for the null space, and you write your solution vector in parametric vector form, you're then the vectors that you generate in parametric vector form, in this case UVW, those vectors generate the null space. They're linearly independent. And so in this case, the script B stands for basis. The basis is going to be the set of vectors u, v, and w. That's your basis for the null space. So the null space lives in R5, and it's actually what we call a three-dimensional subspace of R5, because you have 3 linearly independent vectors that create the null space. We'll be learning about dimension a little later. It's used It's used actually. Well, it's fine. No, it's fine. It's fine. Are there any questions on that? On that example? Who's feeling reasonably good about section 4.3, bases? Okay, Benjamin is good. Ooh, okay, Hung, good. I'd love to get 4 or 5 more like at once, thumbs up, but that might be asking too much. I don't know. Okay, Samantha likes it. Good. Eleanor likes it. Wonderful. Okay, so you get a feel for it. You get a feel. Are there any questions before I stop the recording? Okay.